the agency released a stunning image of the most distant single star ever detected by a telescope. This monumental achievement came after the successful launch and deployment of the James Webb Space Telescope JWST, which marked a pivotal shift in humanity's quest to comprehend the cosmos. As the scientific successor to the Hubble Space Telescope, Webb was outfitted with an entirely new generation of instruments and technologies, enabling it to look deeper into the universe than any previous observatory. Its ability to detect infrared light allowed it to peer through dense clouds of dust and gas, revealing structures and phenomena once hidden from view. When Webb began transmitting its first major datasets, it didn't merely confirm existing astronomical theories, it dramatically expanded the perceived scope and complexity of the universe. These early insights reshaped our understanding of space, time, and the processes that drive cosmic evolution. From its initial observations, Webb offered a breathtaking vista of the cosmos. It revealed a universe teeming with far more galaxies than had ever been imagined, galaxies that appeared not just numerous, but more chaotic and active than previously understood. While earlier telescopes captured faint, blurred impressions of faraway celestial bodies, Webb's high-resolution imagery presented tightly packed galaxy clusters, richly detailed stellar nurseries, and ancient light that had traveled billions of years across space. These observations carried profound scientific weight. Webb identified galaxies that formed shockingly early in the universe's history, some emerging just a few 100 million years after the Big Bang. Such discoveries forced scientists to revisit theories of how quickly matter could coalesce into organized structures like stars and galaxies. The implications of seeing such ancient galaxies were deep and far-reaching. They suggested that the conditions required for star formation and galaxy assembly may have occurred much more rapidly than once believed. In some cases, Webb observed galaxies with defined spiral arms, central bulges, and the presence of dust features that were thought to take eons to develop. This meant that the processes contributing to cosmic complexity either unfolded at a faster pace or operated in ways fundamentally different from current scientific models. One particularly puzzling finding was the presence of supermassive black holes at the centers of some of these young galaxies. Their existence raised difficult questions. How could such enormous entities form so early in cosmic history? Their rapid emergence challenged existing timelines and hinted at unknown mechanisms for accumulating mass. In May, Webb detected the most distant black hole merger ever observed within a galaxy system that existed just 740 million years after the Big Bang. This suggested that black holes could grow through mergers even in the early universe, and at astonishing rates. Another remarkable insight from Webb's early observations was the scale of the observable universe itself. Regions that once seemed empty were shown to contain entire cosmic fields filled with galaxies, stars, and matter. In transition, Webb's enormous mirror, over 6 times the size of Hubble's, and its sensitive infrared detectors allowed it to capture light that had traveled more than 13 billion years. This enabled astronomers to look not just into deep space, but into the distant past, offering a glimpse of the universe in its infancy, along with a panoramic view of its immensity. Each pinpoint of light revealed by Webb was rarely a lone star. It was often an entire galaxy, each containing billions of stars and countless planetary systems. In June 2025, astronomers released Webb's most expansive image yet, a richly detailed view of nearly 800,000 galaxies from the Cosmos Webb survey. This image covered a patch of sky equivalent to 3 full moons seen side by side and revealed more than just vast distances and ancient epochs. It hinted at the dazzling variety and diversity of the cosmos itself. Webb found galaxies shaped in strange and unexpected ways, some twisted and stretched by gravitational forces, others unusually compact, and still others assembling into forms that defied classification. These galaxies were not evenly spread throughout space either. Some regions were laced with immense filaments of gas and dust, forming cosmic webs that connected clusters of galaxies across hundreds of millions of light years. These filaments reveal the underlying scaffolding of the universe, the large scale structures around which galaxies and dark matter accumulate. Within our own galaxy, Webb's powerful instruments penetrated dense molecular clouds, unveiling the earliest stages of star and planet formation. It imaged protostars still wrapped in the gas and dust of their birth, tracing the outflows, jets, and shockwaves that shape their surroundings. In places like the Carina Nebula, the telescope revealed breathtaking details of stellar nurseries, where massive stars were actively carving cavities into surrounding space with their radiation and winds. This unparalleled resolution allowed astronomers to model stellar evolution with new levels of detail and accuracy. In May 2025, a new 3D visualization of the Carina Nebula's cosmic cliffs helped the public grasp the structure of these star-forming regions. Yet beyond the science, perhaps the most profound consequence of Webb's discoveries was how they reframed our understanding of Earth's place in the universe. By showing that the early cosmos was not just filled with galaxies but filled with complexity, Webb underscored how tiny and limited our perspective truly is. What looked like an empty speck of sky to the naked eye turned out to be brimming with ancient galaxies. This realization forced a deeper appreciation of the scale and richness of the cosmos. Further observations included spectroscopic studies of exoplanet atmospheres, where Webb identified molecular traces such as water vapor, carbon dioxide, and methane components that may hint at habitability. While not direct evidence of life, these findings laid the groundwork for future searches. In June 2025, Webb directly imaged an exoplanet named TWWA7b, a gas giant similar in size to Saturn located 110 light-years away in the constellation Antlia. It marked the lightest exoplanet yet seen through direct imaging. Webb's extraordinary sensitivity to faint light variations allowed it to characterize the chemical makeup of planetary atmospheres in unprecedented detail, narrowing down which worlds might be most promising for further study. It also captured gravitational lensing events where massive galaxies or clusters bend and magnify light from even more distant sources. These natural cosmic lenses made it possible to study galaxies otherwise too faint to detect, extending Webb's observational reach even further and offering vital insights into the distribution and behavior of dark matter. In 2025, Webb's observations of the Bullet Cluster delivered the most detailed images to date, revealing a surprising abundance of extremely faint and distant galaxies. Webb also contributed to the field of interstellar chemistry. Its instruments detected complex organic molecules in both deep space and on the surfaces of icy comets and asteroids within our solar system. These molecules, considered the building blocks of life, were found in unexpected locations, suggesting that the ingredients for life may be widespread throughout the universe. In January 2023, Webb discovered diverse ices in a cold molecular cloud, unveiling crucial compounds that could serve as the precursors to life and the raw material for future planetary systems. The fact that such delicate chemistry could be observed across cosmic distances reinforced Webb's role not just as a telescope, but as a bridge between astronomy and the origins of life. Its images didn't just show more stars, they captured the motion of the universe, galaxies in collision, stars being born and dying, and clouds of gas weaving their way through gravitational forces. This dynamic portrayal of the cosmos, enhanced by time-lapse imaging and luminosity changes, enabled scientists to study how objects evolve, interact, and decay over time. The engineering marvel that is the James Webb Space Telescope made all this possible. Deployed nearly 1 million miles from Earth at the Alta-Lagrange point, Webb had to unfold its tennis court-sized sunshield, align 18 mirror segments with nanometer precision, and keep its instruments cooled to near absolute zero. These delicate feats were essential for capturing the kinds of measurements needed to peel back the deepest layers of cosmic history. Webb also revealed details hidden by dust, once a persistent obstacle for optical telescopes. Through its infrared capabilities, dust became transparent, allowing Webb to observe the birth of stars and the mergers of galaxies. In doing so, Dust itself became a source of insight into the processes of matter formation and destruction. With each new image and set of data, the telescope continued to act as a time machine, reaching so far back that it illuminated the very first chemical elements formed after the Big Bang. It gave astronomers visual proof of reionization, the epoch when the universe emerged from its dark ages and stars began to shine. In 2025, dozens of small galaxies were identified as central actors in this transformation, helping the cosmos transition into the structured universe we see today. Webb's discoveries weren't just scientific milestones, they had cultural and philosophical significance. They reminded us that the universe is more ancient, diverse, and active than we previously imagined, and they forced us to reconsider our place in its vast expanse.